Welcome everyone. This is the second lecture on control signals. In the first lecture I've discussed a few techniques that went into using event type signals which don't have a fixed sample rate, and taking those signals into the quasi-continuous signal domain and applying some signal processing operations. And this week we're going to look at essentially modifying continuous signals or quasi-continuous. The reason I keep saying quasi-continuous, or correcting myself to quasi-continuous, is because they're digital signals, which means that they have a sample rate, which means they're not strictly continuous. So let me stop correcting myself from now on, and I'll just use the term continuous signals. So where do we have these signals coming from? Well, in the control domain, it could be anything. I mean, typically it could be analysis of audio signals. They typically come at slower sample rates. It could be sensor data. It could be data that comes from users, interaction. Can I think of anything else? Probably not at this stage. Okay, so it's going to be a bunch of techniques thus, and quite a few max patches. So brace yourselves. So what are we looking at? Well, the simplest thing here will be thresholding. Okay, so thresholding is the term that covers essentially an analysis type operation, which looks at a signal which is in a specific range and essentially determines whether it is within a sub-range. So that probably sounds horribly complicated. What we're looking at typically is larger than and smaller than in terms of comparing values. And typically with thresholding, what you have is one side of this comparison of this conditional, we use this term as well, is an incoming signal, and the other one is a fixed value, and that is what we call a threshold. Okay, so typically if you have a slider between 0 and 127, our generic MIDI range, then you could be looking at whether it is above 100, below another value, operation similar to this. Let's just immediately look at that. So I'm looking for my thresholding patch. I have a few things open and waiting. Here's my thresholding patch. So as I said, we're looking at the left side here now, and I'll talk about the right side in a bit. So we have a slider. It outputs kind of MIDI standard range, 0 to 127. And then typically you use an object box, larger than sign, spacebar, and then the first parameter, which is our right-hand side operator. You can replace it by sending a number here. If it's fixed, you can just leave it like this. And then what this will output, it will output a 0 or a 1, a 0 for false and a 1 for true. Now, other than just outputting zeros and ones, which is what you see here, it is actually outputting these at a very high rate. Essentially, for every incoming number, it will report a 0 or a 1. Okay, so you don't really see it in this float box or integer box because it's 0, it doesn't change, but with a bang, you can see that it's actually sending a lot of values which can break your patch, so it's worth noting that. Okay, so what we have then is the select one object, which will send a bang if the input matches 1, and that's what we get. Now again, we get a bang for each of these values, and we don't get a bang for these values which are below 50. Now if you want to make sure that you get a single bang when you cross the threshold, which is typically what you're after, then what you do is you use the change object, which excludes the number if the previous input number was the same number. So it will output a number only when it's different from the previous number. So this means that it will just not output zeros after each other, but only when you go to 1 it will. So you see here, what you get if you watch this bang here is I get a single bang only when I go across the threshold, and it actually does this thing unidirectionally. So it reports a bang when I go from below the threshold to above the threshold, and if I travel backwards it doesn't send me a bang. If you want a backwards bang, that's not difficult. You essentially get everything else here. You can do a select 1 0 as well, and then you see I have a bang for coming back as well. Okay, so that's your basic thresholding, and then on the right hand side here what I have is a slightly more complex thresholding system, which is what we call a Schmitt trigger. And a Schmitt trigger is a thresholding system which has two boundary values, and typically you have to cross one boundary value in order to trigger. That's called a trigger threshold. And then you have to cross another boundary value in order to reset the system, which is our reset threshold. So what it does, it allows you to create a system which is often useful for sensor signals when there is a lot of noise, typically drum pads or similar things, because you're essentially stopping double triggering. You are making sure that the signal drops below a certain value before it can be triggered again. So in this case I have two thresholds. I have 50 as my triggering threshold, so I'll have to go above 50 in order to trigger, and I have 20 as my resetting threshold, so I have to go below 20 in order to be able to trigger again. So let's see how this works. You're watching this bang down here. So if I'm moving down here, nothing happens. Once I cross 50, I should have had something happen. Maybe I have to reset these things. That's one needs to set like this. Let's both keep them open. Okay, here we go again. So if I cross from below 50 above 50, there was the bang. Okay, and now I can keep crossing the 50 from 40 to 60, what I'm doing now, and I'm not re-triggering it. The bang is not recurring. I have to drop below 20, and then you see the system has reset, and now I can again do a trigger when I cross the 50 threshold, and again it becomes insensitive to the triggering. You have to reset the system and then it triggers again. Okay, shall I briefly explain this? Maybe it's useful. Typically what happens here is, well, that's just lovely max MSP. This is the meaning of it all. Just making a little puzzling thing out of a few simple objects. So the simple objects are as follows. We have conditionals, which I've just explained. We have the select one, which is also clear. And then the one thing which might be new here is this G switch. And what it does, it essentially redirects signal flow. And it's visually clear. If you send the bang to the right inlet, it will go either left or right, depending on the state. And then the point here is that you can change the direction with an incoming number, 0 or 1. So toggle is just sending zeros and ones. I can make this, potentially make this even more clear if I actually send it zeros and ones. Here's zeros, here is ones. So that's how it works. Okay, so with those three objects, a G switch, conditional, and a select one, I can make a Schmitt trigger. So how do I do that? Well, first of all, the incoming value goes to two switches. And what you see is that left-hand side output is not connected. So essentially, I'm not redirecting signal flow here. I'm just interrupting it. Okay, so what this means is that if the switch is turned right, I will be thresholding, I will be checking the incoming value. If it's turned left, I won't be doing it. So that's pretty straightforward. If the system is ready to check for trigger, this is the state of the switch. If it is waiting for a reset, this is supposed to be the change for a switch. Okay, so let's start with it being reset, waiting for a trigger. So it comes in the signal. If it is larger than 50, it reports 1. If it reports 1, then two things happen. Three things happen. These are the three things that happen. First of all, I report a trigger because that's now a legal trigger. We have crossed the threshold. Second of all, I will turn this switch off. That's the 0 here. Make it a bit more visible like that. So I'm switching my own triggering potential off. And then I'm switching the resetting potential on. Okay, so let's look at this happen. This is now ready to accept the trigger. The trigger happens, and you see both switches have made a switch. So once this has happened, I'm insensitive to further triggers, and at this stage, I am actually looking for a reset. So this one, you see, has sent a 1 to this switch, making it switch right, and 0 to this switch, making it switch left. So inactivating, deactivating this one, and activating this one. And now this one is waiting for a value to be less than 20. So while I'm moving around here, it's not. And once I go below 20, then this reported bang is doing two things. First of all, it is disabling the resetting mechanism, and it is enabling the triggering mechanism. Okay, so that's your Schmitt trigger. Can be quite useful for sensor signals, other things as well. Okay, so that was thresholding. Let's look briefly at direction change. Direction change is quite an interesting thing. Just before I go further, briefly, you may remember that last time I've talked about analyzing events in order to get continuous signals. And these two, the thresholding and the direction change, are actually analyzing continuous signals in order to get an event. Okay, so it's quite interesting because if you see the perspective here, typically if I have a thresholding thing, I'm getting an event from motion, and then I can analyze, for example, the density of crossing the threshold, and I will go back to the motion domain, to a quasi-continuous signal. So there's quite a lot of interesting things you can come up with in when you combine these techniques. Okay, so another way of getting an event from a motion will be to detect the change of direction. So this is an interesting thing. I have a friend who's actually practiced kind of controllerist. I think that is a term, controllerism and controllerist. So kind of playing music with basic interfaces, sliders, dials, buttons. And he was very good at playing beats with the slider. So what he has done is he has set up a few thresholds along a single slider, and then had a kick, snare, and a hi-hat. And with some practice, he could actually do quite a few things. And then I've seen this, and I've shown him the direction change, which is an interesting thing because it's slightly more precise in terms of operating a rhythmical synthesizer, playing beats, because on a dial, you don't really, on a slider, you don't really see, you don't really feel when you do this. You can hear it, but it's kind of hidden. You don't know when it's going to happen. If you practice, you can become more precise. Obviously, it might be a musical thing to not be precise. You can be playing wonky beats, kind of messed up hip-hop beats, which is essentially what my friend was doing. But if you want to be precise, direction change is something that you can time much more precisely initially. And actually you can combine these two things as well. So let's see what I'm talking about here. Here's my direction change. So here we are looking at a little patch that will send a bang when I change direction. So as I'm moving forward, nothing happens. When I change the direction, I start moving back, that's when I get a bang. And then I keep moving back, nothing happens. And bam, when I change direction, it goes in the other way. So if you imagine this to be a physical slider, I guess you would agree that, you know, you can be slowly moving it up and be really precise in terms of timing in changing the direction. Okay, so how does this happen? Here is the patch. So first of all, we have a trigger integer bang. What this does, it is a kind of a traffic light type system in Max MSP. So what it does is for every incoming value, it will do two things. It will send a bang and it will send the incoming value as an integer. So that's what I stands for, integer, B for bang. And as usual in Max MSP, everything goes right to left. So first thing, bang happens, second thing, integer happens. And this is quite crucial. This is why it's a nice thing to do. It kind of makes sure that something happens first. I got a bang and I've got a number. So in this case, the crucial thing that's happening is that before the number comes through, I get a bang, which means I can prepare something ahead of this transfer. Okay, so what happens here then is that I first get a bang, I trigger the message box, which will output the stored value, and then I send the incoming integer and store that. So this acts as a memory cell. So for every number that comes in, I will first output the previous number and then store the current number for the next incoming number. So all in all, what I get here thus is a subtraction. I subtract the previous value. So from this one, I get the previous value from the current value. You see, so as I move the slider, what I expect to get then is the difference of the two, something we call a differential, or a step from previous value. So you see, if I move in a positive direction, typically I get ones, but sometimes I get a 0, which means that this slider object has reported the same value twice. Can happen. It depends on the implementation. I believe in this case it's because the mouse resolution is slightly higher than the dial resolution. So you can move a mouse, it reports the movement, but it actually hasn't gone a full step up. You could have implementations when there is no repetition of values. It really depends. So you see it's strictly positive as I move to the right, and then it becomes either a negative value or a 0 if I move backwards. Okay, so that's my first step in determining the direction of movement. Then I use the select 0. So if you remember, select will send a bang if the input matches the specified value. So zeros come out of here, and on the right hand outlet, what it will send out is everything but 0. So I'm actually excluding zeros, which is obviously a good thing here because I get zeros in both directions. So the zeros don't tell me anything about the direction. So now from here, let's verify that, I will get strictly +1s and -1s. Zeros are excluded. If you see, if I move really fast, I get higher values. Fine. And then I'm checking whether this value is positive or negative, and then I'm making sure that I get a bang when this value changes, and this is what happens. Okay, I could get a separate bang for separate direction changes. I could do that with a select 1. Oh, sorry, an object box there. Select 1, because then I will get a bang for one direction, and a bank for another direction. Let's check that. You see I get two different ones. Obviously what I have here, you see, is I'm getting multiple banks. So the change is quite crucial. This one will actually output the number if it changes. So I actually have to feed it from here, and then hopefully I get two separate banks for two separate direction changes. Okay, so that's our little direction change analysis. And then I have two motion analysis patches which will analyze the velocity of the movement and the energy of the movement. Now, briefly, we've looked at similar things. With velocity, what we're looking at is the actual continuous differential of position. Okay, so the velocity of an object is the difference in position at a fixed time interval. Obviously, we're not doing physics here. We're not dealing with seconds and meters, and we're not really interested in the real velocity or speed value here. What we are interested in is an indication. And anyway, if you use this in your system, you're likely to have to scale it up or down based on your needs. So the absolute measurement of velocity is rarely crucial. So velocity is thus the differential of position. And typically, if you have a slider, what you are getting is the position. The actual value of the slider determines or describes where it's at. It determines its position. And the nice thing, the advanced thing to understand here is that actually that's a high-pass filter. So this is how we're linking it back to audio signal processing. I won't go into too much detail here, but typically, if you do this at audio rate, it will do a high-pass filter. And then we will also look at the energy of the motion, which will be the integral of position, which is typically the sum of the current position and the previous position. And you would typically keep the sum going. Okay, so if you have a unipolar signal, I've mentioned this last time, then you would get an infinitely growing integral. If you have a bipolar signal without DC offset, then the growth will be capped. You won't get an explosion like that. So we'll look at that, and then to make the connection to audio signal processing, actually taking the integral, integrating a signal, is low-pass filtering it. Okay, so let's look at these implementations then. Motion velocity. Okay, so what I have here then is a similar patch to what you've just seen, in that I'm subtracting the previous value from the current value. Okay, so same thing, trigger IB, this is my memory cell, from here comes the previous value, here comes the current value, current minus previous. And I get a similar thing that you've just seen. If I go faster, these numbers are larger and so on. I am making this a unipolar signal. I'm offsetting it by 20. Typically it doesn't go higher than 20. Maybe I could get it too. And then what I'm doing is something that I've shown you last time, is I am resampling it. I'm imposing a fixed sample rate on this signal. So I'm storing the value in a message box, and I'm banging this message box at a fixed rate. And this is really crucial because you see the numbers come out of the slider only when something happens. But in order for me to get a velocity estimation, I would have to estimate that it's not moving now. I would have to get a zero velocity. But without any values coming from it, I could never do that, right? So therefore, I'm actually resampling it. I'm making sure that I get values all the time. So this is my actual zero. I've done an offset here. It's not an absolute measurement. And here goes my estimation. So if I move really quickly up, you get a spike there. If I move slowly down, kind of get it slower, up, down. This is my velocity. Now, what you see is that it's not what you might imagine. I mean, if I kind of move slowly down, well, it's just a few negative values, but it's sticking to 0 quite a lot. It doesn't really describe the slow movement. So what you would have to do is you would have to smooth this signal out. And we've looked at smoothing before, and actually we're gonna look at it now as well. But this is what you get, because with a very slow motion, the resolution here is rather weak. So you see I get a lot of zeros, a few -1s. That's the best I can do with this signal with a single differentiator. Okay, so next one up then will be the energy of the motion, which also functions as a smoothing algorithm. And I've shown you previously the smoothing that we looked at this last week, so which was a basic integrator, and now I'm showing you a leaky integrator, which is slightly more useful because it actually can yield the exact value. So what I do here is I'm using a leaky integrator, which will make a huge difference because it will actually follow the input value. Okay, so if I have a low input value, there is a low output value. If I have a high input value, there's a high output value. And essentially what I'm doing is I'm slowing it down, the movement. So if I make a big jump, you see it kind of goes there slowly. And that's what's happening. So the way this one works is, again, with the memory cell. So this is my memory cell here. So what I'm doing is I'm adding the previous value to the current value. That's how I've introduced it as well. Obviously, I have a resampling here to start with. And then I'm adding the two values. And then what I'm doing after that is I am taking that output value, scaling it down, and then using that as the previous value. Okay, so and that's what you get. So with this coefficient, I can actually change the smoothness of this. So if I go even closer to 1, I will, oops, blow it up, please don't blow up, don't blow up. That's kind of blowing up. It's an IIR filter, it's an infinite impulse response thing, so prone to blow up. Hopefully now, here it is back. So what you see here is that it's it has a faster reaction. So I'm clicking away and I get only a few points. If I go further up, so I have to be careful not to blow it up again. 98, I'm already above there. Okay, so you see now I have a longer decay happening there. And that's about it. So this in a way estimates the energy of a signal. Again, it's not physically accurate. I hope you don't show this to any physics experts. They'll probably be angry at me. But what I'm trying to do here is give you a set of tools in order to explore control signals and a set of clues in terms of what these things relate to. And obviously, if you want to dig into the details here, you're very welcome. But I won't spend more time on these right now. Okay, so the next chapter, in terms of transforming continuous signals, transforming motion, will be the transfer function. Now, you've seen transfer functions previously in music tech. They describe the relationship between an input and an output of a system. And you've probably seen it in dynamics processing, in compressors, because they, with the curve, with the compressor curve, you're actually describing the input gain against the output gain. And what you typically get is you have a linear transfer for a while, and then the output gain is capped. I don't know if you remember, I don't want to spend too much time with the audio side of dynamics processing of transfer functions, but it is worth knowing that also distortion algorithms are displayed, presented, depicted using transfer functions. The difference is that with dynamics processing, you're mapping input and output gains, while with distortion, you're mapping input and output sample values. So there is no amplitude follower in between. You're directly feeding samples into the transfer function. And you get more distortion, and it's worth noting that even if you have an amplitude follower, so it's not a distortion algorithm, it's a compressor, it will still distort. And by distorting, it will create harmonics. So in a way, every dynamics process will induce harmonics, and typically every distortion process will do something to the dynamics. So distortion and dynamics processing are tightly interrelated. And it all has to do with the nonlinearity of the system. So it's not the time to go into linear, nonlinear systems. But it was a worthwhile digression. Okay, so why are we talking about transfer functions in the context of control signal processing? The reason is they can be very intuitive and very powerful in the control signal processing domain. So let's revise this briefly. Here are a few transfer functions. This is what a compressor typically looks like. So you have a linear bit. So a 45 degrees line like that is linear. And the reason is that you are essentially looking at the input values along the x-axis horizontally. And you're looking at output values vertically. And the way you figure out what will be the output value for a certain input is that you put your input value on the horizontal axis. Let's say this is your input value. Then you trace that, you push upwards from that point until you reach the graph. And from there, you turn left and you go horizontally to the left. And where you end up here, this is going to be the actual output value. So it's useful getting this figured out. And then if you think it through, this means that a 45-degree line like this, which is actually a y equals x transfer, output equals input, right? If you connect this to math, to the graphs in math, then you understand that actually for every input value, the output value is the exactly same value. That's the thing here. And then you see here, this line is being tilted down. And in that case, what you get is that for an input value, you get a slightly lower output value. You see, this would be the actual exact same output value, and it's slightly lower than that. So everything that goes below the 45 degrees, below the linear graph here, will actually yield a lower output value. Okay, so here is a gate. Typically in audio processing, what a gate does is for a very low input values, there is no output at all. So the output is 0 for these values. And then there is a little bit of transition in order to link up to the linear transfer here again. So no change in input-output gain here. Here is an upward expander, just a revision really. So we have a linear bit, and then above this threshold, what you get is that the output becomes louder than what the input was in that fashion. Okay, so here is a linear transfer. Think about it. If I have a horizontal line, what that does is it makes the output input independent, right? So this means that whatever the input value, if I trace it, I always end up at the same output value. Okay, so this is useful once we get into drawing these transfer functions, which is what we're getting at. And then if you have a vertical line, it actually functions a bit like a trigger, because all the values, all the input values below this line will yield a 0 output, all the values above will yield a 0, and only a single value here will actually yield a full value output. So it is kind of nothing happens, something happens, and then nothing happens again as you move through the input values, which is a bit like a trigger. Okay, so let's look at transfer functions that can be useful in control signal processing. So if you have a straight line like this, which is tilted upward, you get a range expansion. So what you're looking at is the input range is this range of values. This yields 0, this is above the limit. So this is my input range, but my output range is a full range, 0 to maximum. Okay, so actually what I'm doing is I'm expanding the input just like that. So it can be useful. I mean, you might want to have a dial that does nothing here. Typically what I tend to say is that designing dials and sliders in audio, in music tech, is horribly linear and predictable. So it might be a very interesting thing to actually design sliders that do weird things against the edges. So I kind of have a linear thing, dependable thing, and then when you kind of come close to the edge, crazy stuff starts happening. And you can do this with these transfer functions quite easily. Okay, if I have a line tilting downward, I get an inversion, because you see for this input value I get a fairly high output, and for a higher input value I get a lower output value. So as the input grows, the output is becoming lower, and that's a kind of an inversion. And then obviously with the tilt I can control whether it's expanding, compressing the range, and all the rest. So, and you imagine just by drawing this you can actually get these things to do the job for you. So it can be quite useful, and especially the reason why we're looking at this is because if you have an audio process and a slider that's supposed to control it, typically just straightforward connecting it is a bit boring. So you can just connect it through a transfer function and then draw your way through different options. So these are the options that we're looking at, and you can also combine these things. So you can say, well, actually here I want a linear thing, and then after that I want to invert it, and then here I want something weird to happen. And you can draw it all, and it's fairly intuitive. Okay, a few more. Here is how a quantization transfer looks like. So what that means is that a certain set of input values yield a fixed output value, and once the threshold is crossed, then the next output value is coming. This is typically the decimation of your signal. So a kind of a distortion algorithm is produced. This is essentially lowering the bit rate of your signal. I mean, obviously, in many cases, the bit rate of your signal is the exact same thing. You're just simulating a lower bit rate, which means less resolution vertically. Okay, so you're decreasing the resolution of your signal. Can be useful. And then a few more. Obviously, curving kind of speaks for itself. What I've just mentioned, sectioning, meaning that I have different sections. So here I have a kind of a linear transfer. Here I have nothing happening in the middle of the range, and then I have something chaotic happening. I can also produce multiple triggers like that. So there's many options there for you. Okay, so let's look at this. I'm slightly uncertain. Yes, I was right. I don't have it, so I'm gonna have to build it. Let's build one of these. So typically what we use for this is a breakpoint function. Let me see, I'm a bit rusty on this one. Linear. How on earth was this one called? Bloody hell. Maybe I should take a break. You guys want to have a break? Okay, you guys have a break while I figure this out. I'm reluctant to stop the recording and start playing, editing, whatever again. I should be able to come up with this very quickly. It's been a while, I'm not using it. Breakpoint, what on earth am I looking at here? Let's see all the other objects. Images interface should be here. Web panel, drop file, picked control, Saka, great. Images, audio, here it is, function. Okay, here we go. Pause is over. So this is a breakpoint function, and it allows you to create a function like that. There are a few shortcuts here. So if I command click, I get a sustain point, which can be tricky because it is actually meant for envelopes as well. So I won't go into that. If you make an envelope with this, this is where it's going to sustain. And then shift click, I will erase a point. So for my purpose here, I can move it by dragging it, and then I can shift click to erase a point, and it automatically makes a sustain point like that. Okay, so let's try to have a transfer function where I have first a linear bit, then I have nothing happening, and then I have something mad happening, the one that you've just seen. Okay, so how does this work? You input a value here, and then you get a value out here. It's fairly straightforward. So let's look at that. I input a value here, get a value out of here. And then the only question is the range of values. So typically it seems like it's still doing something. So I'm down to the flat bit here at about 411, and then something crazy is bound to happen, and then things stopped. So the range of input values was 0 to 1000, and the range of output value is likely 0 to 1. I can verify that. Actually, as I do this, you see it just there. The x goes up to 1000, y goes up to 1. And that is your transfer function. So it really is simple. I can make this potentially more useful if I make the input domain 127. Okay, so what happened then is that all the other values are just invisible. They're still there. And then let's make this one also 127. Let's see if I can make this work with the regular slider. Here's my regular slider, because it will be visually more easy to understand. Slider input, slider output. Just like most of these objects, if you send it a clear message, it is supposed to remove all the data points. So here we go again. Don't really need a sustain point here. Okay, so some gibberish here, something flat here, and then kind of a linear input here. So you see what happens there is that the slider is joining the input value, then at some point it hardly reacts. Obviously it's not truly flat, and then if I go here, then it starts doing weirdness. Okay, so hopefully you get the idea here. This can be really powerful, and it can be even more powerful if you do what we call one-to-many mapping, which essentially means that you have two or more many, right, outputs with a single input. So in creating music techie stuff, I definitely recommend trying this, because what it allows me to do is have one input slider that does a lot of funny things at the same time. Okay, and because it's such an intuitive interface, you really can tune it to do something cool, right? So if I have a synthesizer running, I can have 4 parameters controlled with a single input slider in many different ways, and as you change these transfer functions, the way it responds will change as well, and you can intuitively create something that is quite amazing. Okay, Those were the transfer functions. We're getting on with this. There's a few things left. So let's look briefly at the large picture here and the larger perspective. In terms of creating music techie stuff, because we've seen most of these things here, we're kind of wrapping up our applied audio systems studies. We've looked at multiple input stages in terms of users. You've now seen how you can actually analyze signals to get these things. We didn't quite look into analysis of audio signals. You probably know things like amplitude following. There are such things as frequency followers. Obviously, you can analyze the spectrum. Once you analyze the spectrum, you can analyze different features. So you can look these things up if you're interested. And then what we've looked at is some control signal processing. So you can actually use those on any of these inputs. And then we've looked at how do you create events from those. Well, nothing complex really, some piano notes, other things, playback. You can do audio synthesis from this, which can be based on events. It can directly be fed from control signals. And then we've also looked at generative algorithms, which are also quite densely interconnected in these schemes, because you can directly control them and then get to hear them or create events that you hear. You can analyze the motion or whatever the input stages is with some kind of control signal processing, and then use that for your generative algorithms, and then go forward and backward again. So quite a lot of ways to connect these things. And I would suggest that, you know, exploring this, I kind of mentioned this last time, it's a useful thing. To understand that you can build a complex system by design. So you can say, well, actually, I have 3 sensors and I want someone to play Mozart with this and variations on Mozart. So there's some generative stuff that plays events which are akin to Mozart's music, and then that goes to a synthesizer. And then because it's 3 funny sensors, I have to do control signal processing to get some very valuable stuff out of that. I may have some things that are directly controlling the generative algorithms. So you can have a complex system by design. But what I'm trying to suggest is that if you understand the potential components in these complex systems, you don't have to think of the outcome already. You can actually experiment quite a bit, right? So if you have a nice synth and you have your interface, whatever that is, then you can really start to explore, okay, insert a few randomizers, different things here, what is the potential there, look at different control signal processing. I mean, transfer functions, what I've shown you just now with drawing your transfer functions, I think it's one of the most potent experimental things. And honestly, I don't see it used much, so hopefully you can make good use of that. Okay, so we're wrapping this up essentially. What we are doing here, what we've discussed here, is something we called mapping already. Okay, so it's all about connecting inputs and outputs. You can make it arbitrary. It is key to creating complex systems, obviously. What I've mentioned is using a single interface for different audio production stages, for different outputs. And you can actually do the other thing as well. You can use many inputs and combine it into a single output. So this is how we distinguish, how we name these things. These are the topologies of mapping. We have one-to-one mapping, means one thing controls one thing. One-to-many, what we call divergent mapping, which is really powerful for complex control. And we have many-to-one, which can be very useful if you have complex generative algorithms. So typically you can come up with a generative algorithm that has 20 output signals, but you have a synth that has only 3 or 4. So you can do similar things to combine these signals as well. I mean, we've looked into kind of interesting control signal processing bits. I didn't go into adding things together, multiplying things, basic arithmetic. I kind of expect you to understand that, you know, that's something that's fairly straightforward and that you can use and experiment with anyway. And then finally, I'll talk briefly about what we consider to be conceptual mapping. So this is the next level, really. So while we are dealing with parameters that are defined by the affordance of a synth, of a generative algorithm range like this, these technical terms, we are not really getting to the next level, which is the level of conceptual mapping. And similarly, while we deal with the input stages in terms of their technical properties, in terms of the position of the slider, the press of the button, the position of the mouse on the screen, the sensor value, these are still rudimentary technical descriptions of what's going on. And the conceptual mapping kicks in when we go beyond these rudimentary descriptions and we describe them in a way that is more natural, in a almost natural language. So typically you would have to create an analysis system that actually tells us a bit more about what the user is doing. Okay, so I can come up with something like, is the user frustrated? Okay, so how do we do this? How do we analyze whether the user is frustrated? Well, we can try to do something with regularity. We can say, well, if his interaction is irregular, if it is very busy, if the density of certain events is high, and so on and so forth. On the other hand, we can also say, well, is the user calm? We can also see, is the user in tune with the system? Is he continuously using the system? So typically everything you come up with in terms of describing the user's activity can be analyzed for. So that's why it's the next level, because we don't really go there. But if you have some ideas, get in touch, and then I'm happy to discuss the feasibility of creating that type of analysis. So that's on the side of the input, and on the side of the output, in order to have a conceptual mapping, you would also have a descriptive term to cover what is actually bound to happen. So rather than change the range, change the whatever, a certain value, a certain parameter value, FM index, whatever it is, you actually use concepts that would be something akin to something that I've just said, really. You could actually have a frustrated sound. You could say what is the piercingness of a sound. So these descriptive things. And in a similar fashion, it is a bit more complex, because you don't just have it's not an accessible thing to have a synthesizer with the parameter called piercingness, although more and more of these things are occurring. But typically we still deal with parameter titles that are technical in nature. So that's where conceptual mapping comes in, because then once you have concepts on the input and concepts on the output, then you create the conceptual mapping, and then you can say, well, if the user is calm, please make sure he wakes up, and if he's frustrated, please make sure that he's calmed down, or anything like that. Okay, so this is just a kind of a highlight. Obviously we won't be going that far, but it's potentially useful to understand this already. Okay, so here is another graph of how things work out in terms of more complex systems. So here I've divided it in three things. First of all, control analysis. So what is the user doing and how we control that. We've talked about these things, so this is a bit of a summary. So we have events and movements. Control analysis algorithms are typically interface specific. So you wouldn't necessarily be able to just change it for another type of interface, because they depend on the physical properties and the electrical properties often of your sensors or interface. Then another interesting term, which is a huge field of research, is gesture following, which kind of goes towards the conceptual domain that I've just described. So typically You know, if you imagine a body tracking suit and you say, well, actually I want to follow the user, and when the user draws a circle, then something supposed to happen. And that's the domain of gesture following. A huge amount of research there, different algorithms, complex stuff that we don't go into right here. And then what I've mentioned as well, you can do this analytically by design, or you can do it intuitively, just taking the modules, the kind of processing, control signal processing modules that we've looked at, and just play out, you know, have some fun with those, see, try to get something useful. Now, I'll now talk about the preset concept, because these are typically source specific in the sense of being the sound source specific. So this is where the audio comes. And typically a preset, a way that the parameters are being controlled, is again specific to your synth, specific to your output stage. So typically you can't really interchange synthesis engines with the presets that are made for those. And presets are really useful because obviously from a large pool of possible settings, you're specifying a few things and you're making it more implementation specific. So you're actually creating a complex system rather than a system that, you know, allows you to do everything with everything. And then in between is something that I would like to highlight, which is what I like to call behavior simulation. So this is interesting because we're looking at things that can be interchanged, right? And that's again going a bit towards this conceptual mapping idea, because here you're actually dealing with a concept arising from the control, and you're dealing with a way of controlling the synthesis, which is also interfaced, right? So typically here you can have conditional reactions, like if something, then something else. And a conditional reaction is not necessarily specific to either of these, right? State transitions typically happen here. If the user goes through certain things, then something else changes, the preset changes. So you can actually imagine a set of transformations which are not interface specific, which are not synth specific. They actually are here in between, creating patterns and things like this. And this is useful to overview because typically when you're building a complex system, the first thing you do is build a complex system. But once you go beyond that, you're starting to look at modular approach, which means that you're building components that are interchangeable. And actually we're already looking at this, because what I've shown you in the last two lectures is a lot of little modules, little control signal processing modules. So it's really useful to be able to, first of all, understand what their function is, and then be able to predict how different combination of these things will behave, and then be able to design something, get a very specific thing as a target, and be able to build it from these building blocks. Okay, so that was the advanced and interesting stuff. I really have no clue why I have the basics back here again, but I think it's because you typically have seen these things before, and I'm just somewhat expanding on this. I won't spend much time with this. You've seen the interesting stuff. If this is any issue, I invite you to get in touch, and then we can discuss this, or if you have problems implementing these things. But I will show you one interesting thing. I think best thing is just to, which is this exponential mapping and all the rest. So instead of following these slides here and talking too much, which is what I've just done, I'm going to just show you the patches that do these things, and that will be the end of it. So first thing is exponentiation. Okay, so exponentiation is taking a value to the power of, right? That's the exponent. So in an exponent we have a base, and then we have the power, and we can just verify that this is doing what we expect it to do. So you probably know a few exponents by heart. Let's say 2 to the power of 2 is actually 2 times 2, that should be 4. Okay, 3 to the power of 2 is 3 times 3, it's 9. And then 3 to the power of 3, I have to re-trigger that, is 27. So 9 times 3 is 27. Okay, so this is the base, this is the exponent, and this is exponentiation. Okay, so the nice thing about exponents is that regardless of the exponent that you have, 0 will yield 0. Okay, so no matter how many times you multiply 0 with itself, you get a 0. And the other thing is, no matter how many times I multiply 1 with itself, I will still get number 1. Okay, so 0 to any possible power is 0, and 1 to any possible power is 1. Now 0.5 to the power of 2 is 0.25, which is squaring, and 0.5 to the power of 0.5 is, I believe, 0.71, something like this, which is square root. Okay, so the interesting thing here is, the thing that we're looking at is that if I'm taking my input value to the power of 1, I'm actually saying that's nothing's gonna happen, I'm just having the exact same value. If I take it to the power larger than 1, then what I get is an exponential transfer, which is slower to rise in the range between 0 and 1, and then catches up really quickly. And when I reach the 1 with the input, it actually reaches 1 as well. So this is a way of creating a curvature in your slider. Now remember, this works in the range 0 to 1. If you change the range here, it will be breaking it. So if you want to use this curvature, what I suggest is first make the curvature in the range 0 to 1, and then do another range conversion, a linear range conversion, if you need a different range there. So that's values larger than 1. I mean, obviously I can crank it up, and then see, it's completely glued to 0, and then only in the last bit it will suddenly jump up. Okay, so again, you can combine this with transfer functions, with one-to-many mapping. You know, you say, well, actually I have a slider that does something in my patch, in my synth, but when I push it in this last very bit, then I want to turn the distortion on and do something crazy, or I want something weird to happen. So you can just do that. And then if you go values smaller than 1 and larger than 0, then you get the opposite behavior. Okay, so this is very close to 0. So it jumps up immediately, and then it is quite slow in allowing the input value to catch up. And again, 1 yields 1, 0 yields 0. So depending on this value here, you get a slightly different behavior. Okay, so that's very cool. That's your curving. Now here what we had then is the input value to the power of a fixed value. What I have here is that the dial, the input value is the exponent and the base is fixed. You see? So I'm taking 2 to the power of my dial value. Okay, and this is what you get. This is a bit funny because I should display the floating point there. So what I have here is a dial which goes from 4 to 14, and I'm taking 2 to the power of that value. And what I get is an actual exponential value which is useful for frequency. You see, 16 Hertz to 16,000 Hertz. This is how you do it. And then what you get is that halfway, I actually get halfway the spectrum. Okay, so this is that thing that is quite challenging sometimes in terms of music tech, understanding how to map a linear control to a frequency value such that it is perceptually adequate. Because if you just control linearly the frequency, what you get is a stupid resolution. And this way you get a really neat resolution. Uh, and the same holds for amplitude values as well. Okay, so this is typically, you see, actually I've called this curving and this exponentiation, which is probably a better choice of terms, but you see I'm getting confused myself. And the thing is that unfortunately in the trade people just use all sorts of terms, logarithmic range, exponential range, curvature, all of that. But what I'm trying to highlight here is that if you want to control the curve, this is the thing to do. The input is the base of the exponent, and if you want an actual exponential mapping, then you want the input to be the exponent and the base to be fixed. By the way, you can use any number here. I've just made this example to make a lovely little frequency dial from a linear input. By the way, in Max MSP you have objects that do this, but we're always trying to reach a bit deeper and understand stuff rather than just use things out of the box. Okay, I have another little control signal processing thing here, which is Cartesian to polar conversion. So xy to distance from the origin and the angle would be the original Cartesian thing. What I have here instead is distance to different corners. You might find this useful. A bit of math. So what I have here is that this is my top right corner, 0. This is my top left is this one, top right is number 3, bottom right is number 2, and this is my 1. So how did I do this? Well, obviously what I get from this object is just an x and a y, 0, 0, 127, 127. And then what I do is I square these values, so multiply with itself. I add them together and I take the square root. So this is my Pythagoras. And then I do this for all the combinations. So here I invert these values. So I get different distances. And I do another Pythagoras, and this is how it maps out. Obviously, if you're interested, you can look to all the values. This is how it works. 4 zeros in 4 corners. And then obviously 127 is the distance of these 2 corners, and this one is more distance. It's at 179. Can be useful. Again, the nice thing is, just accumulate these tools, have this in the back of your mind, because if you say, well, actually, I have an XY controller and it's just boring to do 2 parameters, well, you can immediately get 4 parameters out of 2. And even more so, you can say, well, how about I don't have an XY controller, I just have 2 independent dials and I want something weird to happen. Well, do it. Try these things out. You can intuitively approach these things and create a lot of interesting things. And the great thing about doing this experimentally is that if you create an instrument, a sound process, which is controlled in a weird way with some funny control signal processing, what you will get is typically something that is difficult to explain because it's a bunch of weird things in there. But what we are often able to do is learn to play things that we can't really conceive of. So if I have 5 dials and 20 one-to-many mappings, 3, 15, whatever amount of transfer functions, stupid Cartesian conversions, everything you come up with, and they create a nice synth, I can actually learn how to play these 5 dials without ever understanding what's behind them. And that's the real thing, because then you kind of physically, intuitively learn something and it becomes your instrument. The instruments that are built in a way that you have to understand them first can be really daunting. And if you play such an instrument for an audience, they actually see that you're in the middle of thinking about something. Which bank was it? Which fader does what? You see, so I would suggest that creating instruments which cannot be understood but can be learned are much more musical, because then your physicality is much more important, and your emotions can kind of directly control the sound rather than having to think about, well, how do I make a sad sound? Okay, and which fader was that again? You see what I'm saying? Okay, so we're really wrapping it up. I'm kind of taking a long time to do this, but these are fairly interesting, exciting things, I would think. What do I have here? I have two-dimensional thresholding. Okay, so we've looked at 1D thresholding, and in this case, what I have is a thresholding which works to detect my position in 4 different corners. And I've done this with this stupid kind of logic thing. So I have, first of all, the x value. Let's just look at how this works. So the x value is either smaller than 63 or larger than 63, meaning to the left or to the right. There it's left, there it's right. And then the y value, bottom is 0 and top is 1. Okay, so what I'm doing there is I'm adding these two values, but here I'm doing some extra math. So this one stays 0 and 1. Okay, and then this one becomes, so from 0 I get times 2 plus 1, it becomes a 1. And from a 1 I get times 2, it's 2 plus 1 is 3. So this one is 0 and 1, and this one is 1 and 3. So all the combinations end up being between 0 and 3. Sorry, 1 and 4. Okay, because when this one is lower, it's always 1 at least. So if this is 0 and this is 1, I get a 1. So I get neat little values between 1 and 4. So it's just one of those things, man. I mean, if you were to think about, okay, so how do I do this? And you do this with, you know, there could be many complex, unnecessarily complex way of doing this. And it's just a neat little trick. You can play with these values and get 4 distinct values for 4 different corners. Exciting and cool. Another 2D thresholding technique. So what I have here is I'm looking at whether I am below or above a straight line. So if you imagine a diagonal here, if I'm below here, I get a 1. If I'm above there, I get a 0. Okay, so how that works is that I take the value, I times it by 2, and I subtract 35, and I check whether that value is larger or smaller than this one. Okay, if I invert this, it would be the other way around. Obviously puzzle it out if you're interested. I won't go into more detail. And then finally, I hope you're still with me, a bit of quantization, a bit of rounding. Worth noting, rounding is typically a process that goes to the closest integer, whereas truncating is a process which just removes the decimals. So in some instances this can be of interest. And what I have here is kind of reducing the resolution. Could be interesting. I mean, if you want to play a melody with a continuous dial, obviously, you know, you wanna fix a few steps along the line, many other things. Okay, guys, well, that was it. Thank you for your attention, and there will be one more lecture in this short series when we will essentially look at applying some of these things in a generative music setting, which is next week. Thanks for looking. Bye.